Welcome back. Hopefully everybody's staying safe and healthy and ready for another, well, actually it's not another day. The day's largely over. The end of a day, including some 115. For those of you who have not yet watched today's videos, I highly encourage you to. My daughter is very proud of her impersonation of me or trying to be better than me, I guess is what she said. So you'll have to watch that if you haven't yet. Other than that, today is hopefully a relatively simple day, relatively straightforward day. In the lecture, in the videos, we talked about sorting and went through a couple different real sorting algorithms, the real algorithms actually that they use inside of Python for Python sort. Just so you all know, and I say this in the videos, we're not expecting you to memorize anything. We're certainly not expecting you to have everything, nothing memorized or any of that sort of stuff. The idea is mostly just to see it. We also do talk about searching a little bit. Again, I'm actually going to go over that now. We don't expect you guys to have this code memorized. We're more using it as a way of sort of paying attention and giving you ideas for how to debug code, how to fix code, how to find mistakes, and also to start to set up for the classes that come after 115. So that would be 116 and 191, and then to a lesser extent 250 down the line, where you're going to be looking at all of this sorting and searching a lot more, and there you will be expected to be able to do some of this. So the first search that we talked about in the lecture that we're going to talk about here is linear search. This is a pretty straightforward search. The data can be in any order that you want. There's nothing really required. And the idea is we just want to go and find if something exists. So suppose that we're looking for LP. I just have some initials here because it was the first thing that occurred to me. They don't actually stand for all that much. I don't think I know anybody with any of these initials. But suppose that we're looking for LP. And so what we want to do is go through the list, go through and see if it's there. So we can run this. And what I've done here is I've taken the linear search algorithm from the lecture. So what we're going to do is we've got a list that we're searching through, the target, the value that we're searching for. And then to help us debug and understand what's going on, I've got this variable compares. And that's just going to count the number of comparisons that we have. So what we'll do is we'll say for each entry in that list, we'll increase compares by 1 for the comparison that's about to happen on the next line. Then we'll see if the entry is equivalent to the target. If it is, we'll output that we found it and how many compares it took. And then I have else. We'll print out that it wasn't found, how many compares it took. And so we can run this on LP. And when we do, we see it's not found. We see that it returns false. And obviously that's wrong. And that might be a little bit difficult. But if you look, by having this one compare out there, I can immediately figure out or quickly figure out what I did wrong, right? If compares is 1, that means that this ended that first time through the loop. Well, the only way that that could happen is, well, it didn't match this. We know it was false. So it went into here. So of course it printed out that result and then immediately returned false. And this is one of the points I was trying to make in the video. One mistake I still see a lot of students making, which is you have to remember a function can only return once per call. As soon as we hit that return statement, that function call is over. So here, what we're doing by having that return false inside of here, we're saying, well, if it's not at that first item, then we're never going to find it. But that's not necessarily true. I mean, LP will be there. So what we need to do is move this out of the loop. And so one thing you actually can do, this is legal in Python. I will say it is legal nowhere else, is to move out the else like this. Python has 4 else statements, this else being run when the loop ends. I know of no other languages that do this, and I will be honest with you, this confuses the heck out of me. I would never tell anybody to do this, right? Because you want the else to naturally match up with the if. And so this just doesn't make sense to me. So I'm going to get rid of the else. But then we have to think about where this should go. And the answer is we just need to move this out of the loop, right? So if you think about it, inside the loop, what are we doing? Well, we're going to compare that entry to the target. If there's a match, well, as soon as there's a match, we know that the search should return true, right? We want to return first location where there's a match, or if there's a match. As soon as there is a match, the answer has to be true. We don't need to wait any further. So we can keep that inside the loop. At the same time, if we think about, it's going to add a comment saying loop is over, right? What does it mean when we get out of the loop? Well, the only way we can ever get out of the loop is for us to have gone through the loop, gone through every entry in that list, done this comparison, and never found a match. In that case, well, we've searched everything. That's when we know we can return false. So one big thing to remember, we can only return once. So if you have a return statement inside of a loop, you better make sure that that is definitely the answer and that it has to be the answer, because once you run that return statement, you're done. So now if we run it, you can see that we're going to find LP. It's actually going to take 9 comparisons. We could look for other things. So here I've got to look for JL. Note that JL is not in this list. And of course, if we run it, it won't find it, but it also takes 9 comparisons. It's got to go all the way through, do all those comparisons. If we look for something in the middle, FW, and we can see that's a little bit faster, 5 comparisons. If we do AR, that first one, that's actually pretty quick. 1 comparison, really well done. But now for AA, it also takes 9 comparisons. And this is really one of the issues with linear search. The results for linear search really depend on what we're doing. If what we're searching for happens to be near the start of the list, then it's going to run really, really quickly. If, on the other hand, and you can see here, this is the case, we either don't find it or it's towards the end of the list, we're going to use a lot of comparisons. And so linear search is okay. If our data weren't in order, then actually it's kind of necessary. But while it can be very fast, the problem is typically when we look at algorithms, we look at what their worst case is, right? Like if you had an algorithm that's really, really fast most of the time, and then sometimes it takes longer than a year, that's not very usable, right? We couldn't do anything with it. So we want to speed up this linear search. And right now, if we look at it, there might be a way to do it, right? All of our items here, I think, are in order. And I'm looking at it, and most of them are A, B, C, D, E, F, G, H, I, J, K. No, J, K comes before K, D. I swear, officer. I was gonna say, see, I can tell. What is it? Isn't that what like they do for when you get pulled over for? They think you might be driving drunk or whatever. They make you do the alphabet. So now you can see I am coding completely sober. So now that we have this in order, we can try to take advantage of that. So we have to think about what it means, how we can use this. Well, if we have a match, again, we can still return true. But what if we don't have a match? Well, one thing we can do is we can think about how this is going to change. I'm actually going to change the name slightly. I'll make this ordered linear search, since that's what it is. So if all the data are in order, then of course, if it's equivalent, we know it's true. I know I can't include an else here, right? Because an else would just say, do we have a match initially or do we not? Well, I don't know that yet. I like that I just got a like. Apparently all I have to do is make a joke about drunken coding and people like this video. So I know I need an else if of some sort, elif of some sort. So let's think about it. If the entry that we want is, if the entry that we have, the location we're at, so we're at CD, and we're looking for something greater like LP, we have to continue. But if we're looking for something that starts with B, we know it won't be found because everything afterward is only going to go up. So we can actually take advantage of that, right? If the entry is greater than target, well, what does that mean? First of all, it means we have to add another comparison. Actually, we need another one even if it's not. So we need to add another comparison, and then, of course, it's not going to be found. So what we can do is just copy and paste our not found information. Into here. So we'll print out our result and return false. So the question then becomes, do we ever even need this? Is there any reason to have this last little bit? Well, I'm going to keep the printout there just to check. Let's see what happens if I run it on the examples I have right now. And you can see it actually works. Everything here is correct, right? LP is found, JL is not found. We do have, it is slightly faster, right? We don't have to search everything for JL, I guess. FW is found, AR is found, AA is not found. And note that not finding AA, that happens a lot faster. That only takes now 2 comparisons. That's good. The amount of comparisons needed for AR is reduced. It's only 1 comparison. That's pretty good. But you'll note everything else takes a lot more. Doing this ordered comparison this way can be a little bit better, but not a heck of a lot. And in fact, right now, if I try this, let me just change one thing. Suppose I look for LX. If I look for LX, cut this out, what are we going to find? Note that if I have a search for LX, it never gets printed out. There is still one way that we need something at the end of this loop, right? LX, which comes after all that data. If we go through the entire list and we don't find anything, and that's still possible, we still need to handle that. So now if I add this back in, that code after the end of the loop, then you can see now would be able to handle that. So on the one hand, this ordered search is better in a few cases, like 1 or 2, but by and large, it just sucks. Honestly, no one would ever actually write this search in real life other than maybe in a 115 class because there are better ways of doing it. The linear search is okay, however. I'm going to go back to that. There. Keep the linear search if we don't know that our data are ordered. If the list could be in any order, then that's pretty much what we have to do. But there is a better way for us to go about things when the data are ordered. So that's a binary search. And again, I'm not expecting you to memorize this code. I'm not expecting you to be able to say, oh yes, this is the right code to use. But I would be expecting you in module 4, in the final exam, to understand how this works and be able to sort of give an idea of how it works. So binary search is going to be a little bit faster, but what we're going to do is rather than, it requires the data to be sorted, which means I still need J to be less than K. If our data are sorted, what it's going to do is it's going to keep track of these 2 variables, left and right. Left is the first index that a solution could occur at. So the solution has to be at the left index or higher. And the first index where we stop is right. So it has to be between, between left and right minus 1, that's going to be the range where our solution is. And we're going to be able to use this to actually make things faster. So what we're going to do is we're going to say, while we have a range to search from, we're going to compute the midpoint of that range just by adding them, doing integer division by 2, so going to about the halfway point. And then we're going to do a couple of comparisons. If the target is smaller than that midpoint, well, if the target is smaller, then that means that it has to be on that left-hand side. It has to be smaller than where we are currently. Since it has to be on that left-hand side, what we can do is update the value of our rightmost point to being that midpoint. So we don't have to consider the midpoint. We know that it's too large, but everything to the left of that we might want to consider. So we'll do that. Otherwise, if target is greater than that midpoint, if target is larger, well, then we know that it has to be on the right half of our range. And so what we can do is take left and assign it mid plus 1, move it over by 1, right? And so that way we only consider the right half of our data. Otherwise, well, it's not smaller, it's not greater. It's just like the 3 bears. It's just right. We have a match, right? And so in that case, we can print out, and it just occurred to me, and I did this already once today. I have it printing out BS, which I stood to mean binary search, but I suppose you could take it for something else. But we'll have it print out that the target was found and the number of comparisons. And now what's going to happen? If we find a match, we'll end up finding a match. We will return true, print that out. If there isn't a match, and that is possible, well, that means that, right, what does that mean? Well, it means that we found a place and it can't exist. So we'll either have a situation where right is equivalent to left, or even that right is less than left. So we don't have any range where that value can exist. We know that there's an error. And so in that case, we'll print out that it wasn't found and how many comparisons there are. And you can see one of the things I'm going to do, just to make it easier for you guys to see how this is going to work, and because this is actually a really good debugging technique, is I'm going to print out the solution range each time and actually what we calculate for mid, so I can actually see my progress as I go through this loop. So we can do this first time for LP, right? The one all the way on the end. And if I run this, let me get rid of these because I don't care. So if I run this, right, we start with the range being 0 to 8. That is the entire list itself. So the midpoint is, basically 4. Now, when we compare 0, 1, 2, 3, 4, LP to FW, how am I commenting it out? So I just like to say, whoever just commented, I love everything about this. Not so much the commenting it out so fast, but between Squidward doing dabbing and the name Boo Boo the Fool, that just amuses me. I'm using a shortcut. So in Replit, if you highlight a bunch of code and you hit, so I'm on a Mac. So for me, it's Command Shift. I think it's Control Shift on Windows. It will comment and uncomment right away, that whole block. So there's a way you can just take care of a block of code. And in actuality, so this is true for Replit. This is actually true for almost every IDE. They have a quick way to do that. And a lot of times it is Command Shift. So these are the tricks you learn having done this for a while. So at any rate, so we compare LP to FW. LP is greater than FW. So what does that mean? Well, that means that not only can we eliminate FW, but we can eliminate everything that's below that, right? Everything that's smaller than that. So in this one comparison, we've been able to eliminate half of our data. And so now our range is 5 through 8. So we're going to do the same thing. We're going to add those together, divide by 2. We get a midpoint of 7. which is KD. We do that comparison. LP is greater than KD. So not only are we going to get rid of KD, but we're going to get rid of everything to the right of that. So now our solution range, we're saying if we have a solution, it has to be at location 8. And in fact, it is. And so now it did take us 6 comparisons, but only 6 comparisons. Remember, it was taking us 9 to find this item before. If we have an item that's not in there, so let's try JL. Comment this out. Then you can see again, we'll go from 0 to 4, compare JL to FW. JL is bigger, so we can eliminate everything over there. So now we look at 5 to 8. We're going to compare to KD. JL is smaller, so not only do we eliminate KD, but we eliminate LP. So now our range is 5 and 6. We compare with 6, that is JK. JL is greater than JK, so we've eliminated everything over here. And so we're saying now, in this line right here, the leftmost location we could look at is 7. So it's got to be 7 or higher, but it's got to be less than 6. There is no number 7 or greater that's less than 6. So we fall out of this loop and we say we didn't find it. And note, it only took us 5 comparisons. We're actually able to do this faster. And in fact, if we run this for all of the different values, if we run it for FW, FW is a fun one, right? It takes 2 comparisons. Because it happens to be at the midpoint, what happens is we choose its index, that is 4, as our mid. So we see, is it less than it? Nope. Is it greater than it? Nope. It's, again, that Goldilocks situation just right. We're done. 2 comparisons. That's actually our best case. You know, if we have a really bad case, so like say AA here, right? So smaller than everything. We have to fall all the way off the start of it. It is going to take a while. It will take 4 comparisons, right? We have to start with 0 to 8, so we compare to FW. When we compare to FW, we can eliminate everything there. So then we have 0 to 3, compare it versus 2, which is BS. Get rid of that. We have 0 to 1. Get rid of this, that, get to 0. So this is really a worst case. But you'll note, it only takes 4 comparisons. This is why binary search gets used a lot. You know, its best case is relatively rare, but in fact, its worst case is actually pretty quick. Because we're constantly dividing the amount of data that we're looking at in half every time we check something, we get 1/2 that. What it's going to end up doing is looking at a number of items based on the logarithm of the length of that list. So the number of comparisons we're going to have is based on a log of that list size. And as for why it's a logarithm based on the log of that list size, you'll learn this in CSE 191. That's that math stuff I've talked about before. I don't like it. At one point in time in my life, I know I learned why it's log, and I don't know anymore. Honestly, whenever you see numbers constantly getting halved or doubled, as a computer scientist, the short answer is it's log, and you just do that. For anybody out there who likes math, shame on you. I mean, good for you. We need people who like math, I guess. But there are rules about that. They can derive it. So that's the big thing to understand about both linear search, binary search, you know, both a little bit how they work, what their running times are, and, you know, just as importantly, you know, good ways to sort of track your progress through a program, to add these debugging messages, how to comment really quickly. You know, one thing that I did here is I used this /t at the beginning. That's a way of printing out a tab character. And I did that because that way, if I have a bunch of these, again, use my little trick, and I run this, right? So I've got a bunch of data. I can very quickly figure out which of these solutions, where they each line up with. It's very easy for me to figure out, okay, here's the solution range, and then here's the midpoint, because that's indented even further. So just an easy way of being able to debug code. So given all that, I realize this was pretty short, but do you guys have any questions? Any other things you were interested in, curious about that I can help with? Okay, don't see any questions coming, which is usually when they come. Thank you all. We're going to get back into some more hardcore programming on Monday. All next week, we're going to be talking about databases. We're not going to do a tremendous amount with databases just because it's 1:15, honestly. But we're going to talk about how we can use this idea of a database in our program. Some of you may have heard of them, in which case, great. For those of you who haven't, this is another way that we can store data and be able to use it for a long time. So it's a form of what's called persistent storage. So sort of like a file, text file or CSV file. The difference being that databases are really, really optimized for the computer. So they're much, much faster to use, but a little bit trickier to get used to. So we'll talk about that, however, all next week. With that, I thank you all for paying attention. I hope you all are safe, that you all can stay healthy, that you have a good weekend. Hopefully you get a little bit of fun. I'm actually going to keep my eye out because I'm supposed to be getting a delivery from UPS for nothing exciting, but except for me. So if anybody wants to see me be a big nerd, I think my username on Zwift is Matthew Hertz or something like that. I usually just use my name. I'm not very interesting about that. Anyway, thank you all and have a good weekend. I will see you all later. Bye.